Focuses on planetary science and the origins of life, and he's actively involved in planning for future Mars missions. He is co-investigator of the Huygens probe to Saturn's moon Titan in 2005, the Mars Phoenix lander in 2008, and the Mars Science Lab mission in 2012. He performs field studies in areas of extreme temperatures on Earth, many of whom you might see bits on television, such as in the Antarctic dry valleys and the Atacama and the Sahara Desert. This research simulates a Martian environment. In this presentation, our speaker will discuss the expanding criteria for a habitable world, taking into consideration the numerous extrasolar planets discovered so far and the prospect of discovering moons orbiting these new planets. Chris McKay believes it is timely to reconsider the possibilities for habitability in our solar system and on extrasolar planets and moons, and also how scientists determine the attributes and the search methods for detecting habitable worlds and the evidence for life. Join me in welcoming Chris McKay as we learn about his recent research.
Thanks. I guess Linda just read the abstract I sent her. You could tell I must have been in a stuffy mood when I wrote it, but let me get started now with that device, and then let's see if I can find my slides and start that too. Great. Yeah, good. So I'm going to talk about habitable moons. As those of you in our solar system and beyond, and this is this month, and that's me, and I'm at NASA Ames, and I think the batteries are going dead, which is okay. I have a spare set here. Meanwhile, no, I just, no, can you just put these in here? I only have two hands, and neither of them are very good. It was exciting to hear that Lisa Quintana is going to be here next month. She'll be talking about this in much more detail. This is what Kepler is searching for primarily, planets in the Earth-like planets in the habitable zone. And the habitable zone is defined with this green disk. This is our solar system, and Earth is in the habitable zone. That's very good. That's the answer in the back of the book. If your habitable zone didn't include Earth, go back and recalculate it. Mars is also in the habitable zone, interestingly, in this diagram. And it's based on our experience on Earth. And the sun, it defines the habitable zone. Keep in mind it does two things for Earth. It keeps us warm, and it provides energy for photosynthesis. We'll come back to that. Tilt it. It seems like it's getting too loud. It provides sunlight and energy. Sunlight for photosynthesis and sunlight for keeping the Earth warm. So when we look at around other star systems for planets, it's logical to ask, are they in the same orientation with respect to their star as the Earth, the habitable zone? And these are two systems that were discovered by Kepler, and in fact, Lisa Quintana wrote the paper on this one, Kepler 186, and she's probably heavily involved in this new find, Kepler 452. But I'm not going to talk about those. What I'm going to talk about is habitable zones that aren't Earth-like, habitable zones that are due to a moon orbiting a giant planet. And there's several motivations for why I think we should consider this, not the least of which is science fiction. Liz loves these worlds. My buddy Kim Stanley Robinson just did a book, Aurora, where the theme of the book is colonists fly to a nearby star, Tau Ceti. It takes them 160 years to get there. And they find a moon. They find a moon called Aurora, and it's got oxygen but no life. I don't know how he figured that out, but it's got oxygen and no life, and they try to settle it and terraform it. And of course, Pandora in the movie Aviator, as you remember, was a moon, right? So moons are habitable moons are now the way the science fiction scenes are unraveled. So we might as well start taking them seriously. But in fact, we've been interested in this for a long time. I went back and dug out an old paper that we wrote just after I started working at Ames with Ray Reynolds and Jim Castings, and basically took the models that we had of Titan and Earth and Europa and just cranked up the heat on them and the atmosphere to see if we could make habitable Earth-like planets in what we called then the tidal habitable zone. So here's the star, and we had RHZ, the regular habitable zone, and then we had a tidal habitable zone where the heat that keeps the planet warm is no longer coming from the star, but it's coming from tidal heating. But there's not enough light from a giant planet to do photosynthesis. So it still relies on the light from the central star for photosynthesis, but the heat that keeps the planet warm is coming from tidal heating. This actually points out one of the poor design features of the Earth, is that we have to get enough light to keep warm, but that's way more light than plants need to photosynthesize. Most plants don't want full sunlight. I was out a couple days ago and it was extremely bright and extremely hot, and I was lamenting that we didn't live 10 AU away from the sun instead of 1 with a gentle, consistent heat. And one thing that these science fiction writers haven't quite got into is if you lived on a planet in the tidal habitable zone and it was tilted, say like Titan has got the tilt, a tilt very similar to Earth as a result of Saturn's tilt, there will be seasons. So Titan, if you lived on Titan, you'd have seasons of light, but not seasons of temperature. So you could have the change of seasons without snow plows and baking in the summer. So there's a lot of, I think, directions to explore on the suitability of habitable moons and their superiority to Earth-like planets with all the problems with that. So I'm hoping the science fiction writers will explore it. And the other motivating point, this is what really was in my mind when Linda contacted me. I was working this summer with a student on Titan, the largest, most Earth-like moon in our solar system. It's not the largest moon, but it's the most Earth-like moon, and it's close, it's only second largest. But it's got a thick atmosphere, and we were calculating how we would detect such worlds if they were exo-worlds or exoplanet moons, exoplanets or exomoons. And it turns out the way you can learn about an atmosphere with Kepler, for example, is by watching it move in front of the star and looking at the absorption of sunlight by that planet. And it will appear to be slightly different size at different wavelengths. Right? So the disk that it cuts out of the star will be, for example, bigger in the UV and smaller in the infrared. So you can learn something about the planet that way. And what the student was finding was you can't learn anywhere near as much that way as you can learn by just looking at the planet directly, direct imaging. The way to understand exoplanets is direct imaging. It's not popular right now because transit spectroscopy is all the rage, because virtually all the planets we've discovered around other worlds were discovered by the transit method. So everybody's looking at transits and transit spectroscopy, but what we found, somewhat to our surprise, is that you get much better information if you just can image the planet directly. And I guess that's not too surprising intuitively. It's the difference between looking at something directly and looking at its shadow. Well, imagine now you're looking at our solar system from very, very far away. The Earth at 1 AU is in 10 times more of the sun's glare than Titan being out here at 1 AU, at 10 AU. So Titan would be, the biggest problem with imaging extrasolar planets is separating them from their star. Well, Titan is going to be 100 times easier to separate from the star than Earth is. Now it's half the size, so that makes it twice as difficult, but it's still a big win, smaller and further away. And it's well separated from Saturn. It's 25 Saturn diameters. Question?
I've never thought about seasons on Titan. Does it depend on how long Titan takes to orbit Saturn?
No, the seasons are set by Saturn's. Titan is, as you can see, it's in Saturn's equatorial plane. It's tidally locked. It has no tilt with respect to Saturn. It goes around every 16 days. That is the solar cycle, so the sun would rise and set in 16 days. Then the seasons will be set by the tilt of Saturn, which is very close to the tilt of Earth. And so Titan, the sun would appear to move up and down by 23 degrees over the 30-year-long Saturnian year. Right, so seasons would be longer. They would just be milder. Okay, so this is a preamble of why I think it's interesting to think about extrasolar moons as well as extrasolar planets, and the possibility that when we finally develop the technology to image these worlds, we will be imaging moons as frequently as planets, whereas right now our technology for detecting them is limited to, it favors planets, although people are trying to find moons by the transit method too. So what are the moons and the planets of our solar system of interest here? So here are my favorite planets, Earth and Mars, of course, which are regular habitable zone worlds. I don't mean to diss the habitable zone, the Earth-like habitable zone. You know, I like Earth. You know, some of my best friends live on it, right? And Mars is cool too, literally and figuratively. Of course, Pluto, I had to put Pluto in there because it's not a dog. As we saw from the recent results from New Horizons, it's really a great planet. So hooray for Pluto. But then here are the ones I want to talk about today. These are the moons, the interesting moons of our solar system. So Titan, the big one with the thick atmosphere, Europa, pretty big with an ocean, and Enceladus. Now, when I was pulling down images of these moons, most of the images have them all the same size. You know, it's a common feature, I guess, in depicting worlds is to make them all the same size. Usually when you find images of Mars and Earth, they're also shown to the same size. They're not the same size. Enceladus is tiny compared to Europa and Titan, which makes it all the more curious that it is probably, from our current understanding, the most habitable of the moons. So what I'm going to talk about is these three guys. Obviously, we know about them on Earth. We know about them from our solar system, from studies from Earth and from spacecraft. But they are models of what we might find orbiting other stars. We may also find Mars-like and Earth-like planets orbiting other stars, orbiting other giant planets that are orbiting other stars as moons. We know that these can be moons because there are moons, but we don't see any reason why these couldn't be moons also, right? So you might have an Earth-sized planet orbiting a super Jupiter around another star system. So keep that in mind, even though I'm going to only be talking about Titan, Europa, and Enceladus today. So let's start with Europa. As all of you astronomers know, it is the brightest of the Galilean moons. You can pick it out. If you have a good night, good scope, you can just look at the moons, pay no attention to the ephemeris, and you can tell which one's Europa because it's the brightest. It really is visibly brighter than the others, so try that. My most memorable time doing that was actually once I gave a talk at the Fremont Peak, the astronomy club that meets there, many years ago, and after the talk we looked through this telescope, and I of course didn't know anything about where the positions of the planets of the moons of Jupiter were, but I could pick out Europa just by looking through the telescope. That was really pretty cool. So try it, and that's because its surface is being recovered with ice. And we have very convincing evidence that there is an ocean on Europa. I should scratch the word possible. It really is an ocean on Europa. The evidence is so good that you could not justify a mission to Europa whose goal is to confirm the ocean, because that just is redundant. We know it's there. And the evidence comes in two forms, somewhat surprisingly. One is icebergs on the surface. We see things like this that look like icebergs sticking up. The simplest explanation for these is they were floating at one time. They may still be floating now, but that doesn't prove that there is an ocean now. It just proves that there was an ocean at one time when these icebergs were floating before they froze into place. The evidence that the ocean is still there today actually comes from the magnetometer. As Europa moves through Jupiter's magnetic field, it disturbs that magnetic field. It disturbs that magnetic field in a way that indicates that Europa has within it a large conductor, electrical conductor. This is the same physics that's used in the old style metal detectors, the ones that you would walk through, that detected the presence of metal by a time-varying magnetic field, which is why they could detect any metal, not just iron. They didn't detect magnetized metals or magnetizable. They detected anything that would conduct electricity. And as you walk through the magnetic field induces currents in that conductor. Those currents create magnetic fields, and those magnetic fields perturb the imposed magnetic field, and the magnetometers pick it up, and that's how they detect metal. Well, Europa is doing the same thing. Now, Europa does not have a giant pair of nail clippers inside it that's setting off the metal detector. What could it be inside it that's causing it to respond like a conductor? Well, a salty ocean. So it's clear, and it's doing it right now, and this is the compelling evidence that Europa has a salty ocean, slightly salty ocean. This is the same evidence for an ocean that's applied to Ganymede. It's the magnetic field, and people have recently argued that there might be evidence of this, I think, on Ceres, magnetic anomalies that are traced back to an ocean.
Can that be separated from an iron core?
It can, by the extent of it, and by the fact that Europa's density, we know that it has an iron core. It's a very tiny one. So I can't justify the calculation myself, but the folks that are studying the magnetic field can rule out it just being due to a magnetic iron core. Obviously, if Earth was moving through a magnetic field, its dipole field would interact with that field, and that is due to its convecting iron-rich core. But there's no reason to think that Europa has one of those. Okay, so the problem with Europa, though, let's go back a couple images, is that the ocean is underneath this thick layer of ice, kilometers thick. So it's very difficult to imagine getting a sample and searching for life on it, which is what, in a sense, is my job, is searching for evidence of life on other worlds. So the best chance we have on Europa is on the surface. If there's an ocean, if the ocean has life, then these surface features we see on Europa may be ocean material coming up through the cracks on the surface, and they may carry evidence of any life that's in that ocean. So that's our best bet right now. And the next mission that NASA would like to do to Europa will not land, will not try to get through the ice. It will just map out the surface to try to pick a site that we might go to later. We're actually running into problems with that. Basically, there's a you're going to go all the way there and not land sort of reaction to this coming from Congress. So it'll be interesting to see how they make it work out, especially since it's an incredibly expensive mission. The other world, let's move out to the next part of the solar system, Saturn. Enceladus is a recent star in the astrobiology constellation. It was discovered, it was confirmed that it had a plume of water coming from the South Pole in 2005 as Cassini flew by. Now, I won't say that it was completely unexpected. Some people had predicted that it would be there. In fact, there's a nice artist's conception of the plumes of Enceladus done in the 80s by the space artist Michael Carroll. And the argument for it was the E-ring of Saturn. Again, all of you astronomers know, you look at Saturn, you can pick out the rings. The E-ring is in an unstable position. There shouldn't be a ring there. It's in the same position as Enceladus. It should be removed by Enceladus very quickly. So the explanation was, well, it must be sourced from Enceladus. And so there must be plumes of ice coming out to create the E-ring. And so the evidence we have for the stability of the plume on Enceladus, for the longest evidence, is in fact the E-ring observations, which began some 70 years ago. Direct images of the plume only began 10 years ago now. So we have 10 years of direct imaging of the plume by Cassini, and we have 70 or so years of imaging of the E-ring in terms of constraints on the lifetime. We're now building bigger telescopes, particularly ones that are designed to focus to image exoplanets. And in fact, today, another grad student had a meeting with one of the astronomers to see if those telescopes could start imaging this plume. It's not what they're building them for, but it's looking like ground-based telescopes, particularly the Gemini set that's being built in Chile, near Paranal, will have the capability to see the plume of Enceladus, we think, and then we could track it. And this is important because if we're going to send a mission there, which is what I'm going to talk about in a minute, from the time we start spending money to the time we reach Enceladus is typically 10 or 15 years. If the plume goes away in that time, that's going to be a bummer, right? So we'd like to have some way to monitor the plume, to convince the funding sources that it'll still be there and that we'll be able to tell that it's there and so on. It's sort of a funny story. That's what happened to Titan's ocean. From when we started building the Cassini boat, the Huygens boat, to when we got there, the telescopes revealed that the ocean wasn't there. But by the time we landed, we sort of had erased that part of the mission history. Well, we know that the jets on Enceladus are coming from liquid water below the ice, and that liquid water is in contact with hot rocks. We know that because Cassini fortuitously has been able to study the chemistry of this plume. So imagine this. This is one of the things I love about planetary science. We have a mission going to Saturn. We don't even know that there's plumes on Enceladus. We don't design any of the instruments for it. But we get there and we find these plumes, and so we route the spacecraft through them, and we start using the instruments to do things they weren't intended. We even damage one of them in so doing. But then the most exciting results from the Cassini mission, all total, come from that unexpected and adaptable strategy. It's really a lot of fun. And we've been able to measure the organic composition of the plume. I'm going to talk about that right now. This is just another image showing the plume and its size compared to Enceladus. The organic composition of the plume is perhaps the most interesting thing we've been able to measure on the plume. With a simple mass spectrometer. This is not the mass spectrometer one would like to use to measure organics, but it's telling us a lot. A really interesting thing about the plume is that it has both methane and ammonia. And I'll come back to that when we talk about the Antarctic analog. You know, it's actually odder than you think, methane and ammonia. But it's got a lot of other organics. It's got argon. It's a soup. It really is a soup. And there's also mineralogical information we've learned that tells us that this is coming from a hot vent. So it's really all the major requirements for habitability: water, liquid water, chemical heat source, energy source, carbon, organic material, and a source of biologically available nitrogen. They're all there. It's the only place where in one mission we've gone all the way to the next question being, is there life? There's really no other questions we can ask about Enceladus that to lead up, unlike, say, Mars and Europa. You know, Mars, we're still pecking around looking for organics. Right? Europa, we haven't even gotten to the surface yet. So we got many more steps on Mars and Europa before you can really say the next question that makes sense is life. Enceladus, we're already there. It's the only world in our solar system where we're already at the life stage of the search. And even better, free samples. Right? Coming out into space, plume. And those samples contain organic material. They're coming from a habitable ocean. Right? So it's sort of a no-brainer. Where should we go next? Well, how about the plume of Enceladus? Okay. But first, let's back up. Given liquid water on Europa and Enceladus, is there a plausible origin for life? So this is probably the hardest question we can ask. It's the hardest question because we can't even answer it on Earth. We do not know how life started on Earth. We don't even know for a fact that it did start on Earth. We know for a fact that it is present on Earth. Just look around the room. But we don't know for a fact that it started on Earth. Most scientists in the field just assume that. They usually assume it without questioning. But if you look at it rigorously, there's no data that points to the origin of life occurring on Earth. And indirectly, there's some data that points to it not occurring on Earth. The very rapid appearance of life on Earth right after the formation of stable sediments and liquid water, and the complexity of the first life forms on Earth. Least common ancestor looks like if you look at the history of life on Earth, it appears like Athena from the head of Zeus, fully born. It's really quite remarkable. Some people say, well, that just means when life got started, it really got started. Some people say, well, that means because it came here from somewhere else. So we can't really resolve that even on Earth. And now we're going to try to say, well, could life have started on Europa and Enceladus? Well, given that we know nothing about Earth, we can know nothing about Europa and Enceladus as well. So what we did is just take all the theories for the origin of life, just list them all that have been proposed for Earth, which illustrates the fact that we don't have a consensus theory for how life started on Earth, and then said, okay, well, which ones of these would work for Europa and Enceladus too? And a lot of them would, and particularly this one, where life starts inside of a hot vent. And that would be sort of this decade's most popular origin of life theory. So who knows? The real question about the origin of life is we don't know. The real answer to the question is we don't know how it started on Earth. We don't know if it could start on Europa and Enceladus. That's part of the reason to go look. The second question, could there be a plausible ecology? That's much easier to answer because we can go to places on Earth, and I'll show you some, and point to places where the ecosystems are doing the sorts of things that if ecosystems were doing on Europa or Enceladus, they'd be doing just fine. And in particular, the best story involves hydrogen and methane and CO2. Biology just loves to take hydrogen and CO2 and make methane from it, methanogens. It loves to do that, and methane can be decomposed back into the hydrogen at high temperatures. So you can have a little cycle going where the bugs eat the hydrogen and CO2 and they make methane, and the methane gets reprocessed in the core by the hot rocks and produces back the hydrogen. And it just goes and goes and goes. It's not a sunlight-based ecosystem. And we have to go to places on Earth that are isolated from sunlight to find this stuff happening. But we can do it. So we are pushing for a sample return mission to Enceladus. We want to fly through the plume with a Stardust-like mission and collect the sample. We're proposing it as a joint U.S.-Japanese mission. And the reason for that is the only two space agencies that have done sample return from beyond the moon, from beyond the cislunar space, is the U.S., Stardust is our success, and Hayabusa, the Japanese mission. So they are really into sample return because of the success of Hayabusa. So I am learning Japanese. And the programmatic model we're using is Cassini. Cassini was an incredible programmatic success. The U.S. built the orbiter and Europe built the probe. And it was a clean interface. Each mission had a significant science of its own and allowed, it just was very good programmatically. It's also good in the U.S. because if we take the cost of this mission and split it, then it fits in the discovery cap. We don't have to propose a flagship. We don't have to propose a new frontiers. We can propose it as a discovery mission. And that, for bureaucrats like me, that's very good because it allows us to just propose it without it being anointed by some august committee or another, which is the way the other types of missions have to be. Discovery is the only program in NASA where you can just propose some idea without, and it's judged purely on its merits. It's not judged against a list of approved ideas, which the other missions are, right? Other classes of missions. So this is an artist's conception of what that mission might look like. You know you're serious at NASA when you have an artist's conception of your mission. But even better, you know you're serious when you have an animation of your mission. Now that's big time. So this is an animation of the US orbiter dropping off the Japanese probe, which flies through the plume, deploys aerogel catchers, gets the sample, and then comes back to Earth. And this, the probe is named Siwa, which is the name of the Japanese Old Faithful. Their big geyser in Japan is called Siwa. So that's the concept we have. The US orbiter would fly out there, do in situ science like Cassini's doing, orbit Saturn, deploy the probe, which would be like the Hayabusa, and it would just, the Japanese would then fly it back to Earth, and we would get a sample that way. So it's a nice, clean separation. You can see why I say the Cassini model is our programmatic model. You have basically two spacecraft joined together. And if in a NASA proposal, when you have an international partner, you always have to say, well, what will happen if the international partner fails to show up? I mean, NASA, in the past, it's usually NASA that fails to show up, but never mind. You have to, what will you do? Will your mission still be important science? So the orbiter by itself will do science. So we don't have to have the sample return. We just get better science if we investigate in situ and bring a sample back. They complement each other because you can measure things in situ that you can't bring back, like water, for example. And you can bring back things that are very hard to measure in situ, like heavy organics, the remains of biology. So I've been talking about Stardust and Hayabusa, but the US did another sample return called Genesis. And this is a picture of Genesis. And this illustrates a very important point, which is the challenge of returning to Earth an astrobiology sample which might contain life from a habitable world. Genesis crashed, you may remember. Stardust didn't, which is why our programmatic model is Stardust and Hayabusa. Neither of them crashed. We don't, Genesis? Who's Genesis? Right? But the point is, Hayabusa, Stardust, and Genesis all came from what are called unrestricted back return objects. The Planetary Protection Police didn't care what we brought back from those worlds because they were deemed to be not hospitable to life. Bring back a little piece of an asteroid, doesn't matter. You don't have to sterilize it, you don't have to worry about it, you can just bring it back, unrestricted sample return. Stardust, piece of a comet tail, Genesis, a piece of the solar wind. Not very interesting for astrobiology directly in terms of life, so there was no restrictions on their sample return. But we are bringing back a sample from a world that we are sure is habitable, and the sample is coming fresh from an ocean that we think is very much like oceans on Earth. It is not going to be an unrestricted sample return. We have to meet the most stringent requirements for sample return for that sample. Something like this is not recommended. Right? Not a good idea. So this is in fact the biggest problem we have right now with this mission concept. It's not getting there or doing the collection or heading back to Earth. It's the last mile problem, as they now say. It's the last mile getting it to the surface of Earth. The last mile. It's actually a little more than a mile, but figuratively speaking, you know what I mean, the last mile problem. So how do we solve this problem? There's two possible solutions that at least I've been advocating. One is astronauts. They go meet the sample in orbit. You bring the sample back to orbit. The astronauts go up and meet the sample, put it in a bag, and bring it back. Now that has two really big advantages. One is you're bringing it back to Earth in a human-rated vehicle. The testing and rating requirements for a human vehicle in NASA are much, much more severe than for any non-human rated vehicle. And second, you've got humans there. If something goes wrong, if the parachute doesn't deploy because somebody put the switch, the gravity switch in backwards, the pilot will notice and hit the manual override. Well, there was no pilot in Genesis, and when the parachute didn't deploy, no pilot pushed the manual override. So you have a human-in-the-loop safety system. And that is in reality a better system, and it's also perceived by the public as a much better, safer system. So this is really the solution I like. Plus, having astronauts involved allows us to benefit from what I call the Hubble glow, right? 90% of Hubble's enthusiasm in terms of the public is the fact that the astronauts went up there and fixed it, right? Astronomers liked it too because the bills for those repairs went over to the human space side and not the astronomy discipline scientists. So it was a win-win all the way around. It gave the astronauts something to do. It created an appearance that NASA works together, and the science budget benefited from the money being spent on human exploration. We would get all those benefits by having the astronauts bring the sample back. Human-assisted sample return. But the problem is we're not allowed to say that. When I write a discovery proposal, that part of NASA is a different part of the program, and I can't propose to include it in my proposal. It's, we're stovepiped. We can't include astronauts in a planetary mission. So that would have to be a decision made at the top and then pushed down rather than from a proposal pushed up. So we're trying Plan B, which is a robotic entry system that is 100% fail-safe. Not 99% or 99.9%, but 100% fail-safe. So how do you design something that's 100% fail-safe? Well, this reminds me of the safety courses that we take at NASA, and they can be boiled down to this. Don't move, don't think, don't make any decisions, and you will be safe, right? It is a 100% fail-safe system if it doesn't have any parts that move or must move. It doesn't have to make any decisions or think about anything, right? That's the key to safety. Remember that. Don't move, don't think, don't make any decisions. And you'll be surprised how many safety classes basically take that approach, even if they don't realize. Well, you say, well, how can that work in an entry system? Well, that means no parachute, no deployable mechanism. It comes in and lands at terminal velocity, but you've designed it to survive terminal velocity. You are inspired by meteorites, which deliver organics to Earth intact every day without parachutes, without fins, or without any deployable mechanism, without even a computer on board. Meteorites deliver organics. The Sutter Mill meteorite, as you remember, 2.5 years ago, delivered organics to Sacramento, landing in a parking lot, intact, big chunks, right? So they land like a meteorite, survive landing. You design it that way. Small, compact, the sample's small, you don't need to bring much back. You design it with crushable materials. So there's no brains, no smarts, no decisions to be made. The only thing it has to do is obey the law of gravity and fall to Earth, right? And we can be pretty sure that that's 100%, right? So that's our current approach. Hope that the astronauts will come in and say, let us do it for you guys. But if not, we have at least a proposable, defendable scheme, which is bring it back in a system that has no moving parts, no deployable mechanism, and no onboard computer. It just comes in and goes straight. The other advantage of that is it's a lot more predictable where it's going to land. You can be right there knowing that it's going to come straight in. The problem with Genesis and Stardust is once they get on the chute, they go with the wind and you never know exactly where they're going to come down. And so you've got helicopters circling around looking for them. But if it comes in ballistic, that's like an ICBM. You know right where it's going to go. And you can be there with your mitt to catch it. Now, if the Japanese bring it back, they will bring it back to Australia, which is where they brought back Hayabusa. And then what we have proposed is that the sample would be met by this ship, the Chikuyu, which has a biocontainment facility built into it. So rather than spend umpteen millions to build a special dedicated biocontainment facility in the desert, we take the ship and park it at the port where they take the iron ore that they drag out of the desert, and it sits there safe in port. The sample is carried to the ship and analyzed, confirmed that it's in fact nothing dangerous, or if it is anything dangerous, it's died. And then the sample can be released and the ship can sail back to Japan with their half of the sample, and half the sample gets shipped back to the US. So another big problem with sample return is this containment facility. We just use an existing one, we just float it to where we need it and catch the sample there. And it illustrates another advantage of involving the Japanese is that they have a mechanism for returning samples that they've shown with Australia, and they have technology in their ships to do it. So they take care of that part of the problem. So,
Out of curiosity, why does that ship have a containment facility?
well, they study organisms from the deep sea vent, and they don't know if they're pathogenic or not, and so they want to, for scientific reasons that deal with oceanography, they have a containment facility. Right? Okay, so just a little bit of a word chart here on why sample return from Enceladus. People ask me, other scientists ask me, well, can't you just search for life in situ? And the answer is yes, of course we can search for life in situ. And in fact, if nature conforms to our expectations and life on Enceladus uses amino acids, as I'll argue is the way we would search for it, and these are present in the plume as a distinct group of definite chirality, then there's no need for sample return. We can do everything we want to do in situ. Right? So we have this hypothesis, which I'm going to show you in a minute. If that hypothesis about life is true on Enceladus, then we can answer that with an instrument on board and fly through and not have to bring the sample back here. But nature does not have a good record of conforming to our expectations. Example, perchlorate on Mars. So if life on Enceladus has unexpected chemistry, it's not what we expect, then understanding this will require iterative investigations, which is virtually impossible with in situ methods. So we need to learn to do astrobiology sample return, is my bottom line in red. Right? So let me go back now to the background. What would I do with the sample first? And I would propose to do it in situ. And as I said, if life agrees with our prediction, then we'll actually have an answer to the question. So how do we determine if the organics on any of these worlds is alive? Right? Well, if it's like us, if it's related to us, it's easy. You can look for DNA. And if we find DNA and it's got the same coding and same conserved parts as DNA on Earth, well, we found life. It's not very interesting because it's just more of us. Right? We have plenty of us already. Right? Nothing personal, but I'm looking for something different. Right? If it's alien, then we don't know what to look for. Maybe it doesn't have DNA at all. Right? It makes kind of silly to look for DNA. You do PCR, put in primers, and it doesn't even have DNA. Right? So that's the interesting case, but it's the harder case. So what do we do? This slide should probably have been earlier. What are we looking for? We're looking for something that is alien, something that is not on our tree of life. Okay, that's the prize. And Enceladus is a good candidate for it because it's so far away. So what can we do? What can we search for? Here's a list of possible targets that we could search for. We could search for lipids, nucleic acids, proteins, amino acid selection, special molecules, fossils, da-da-da-da-da. The one I think that we ought to search for is the one that's underlined, amino acid selectivity. I'm going to explain what I mean by that. Amino acids, of course, are what proteins are made out of. So the proteins in your body are made out of amino acids, and life on Earth uses essentially 20 of them. So think of it like a Lego kit with 20 different colors of Lego blocks. And you stack those together to make the proteins that are in your body. And you stack them in different ways. You can make literally an infinite number of different combinations of proteins. Well, combinatorially infinite number of different proteins from stacking them in different ways. So it's basic building blocks, 20 of them. And the diversity in life comes from the way they're put together, the combinatorial ways. So that's what we're proposing would be the same on life elsewhere. One subtlety to this is that these amino acids come in two-handedness, right and left-handed. Life on Earth only uses left-handed ones. So life on Earth is left-handed at the amino acid level. We do not use right-handed amino acids in proteins. So this means that the amino acids in biology, there's been a series of decisions made by biology over the history of the creation of life on Earth. It uses 10 simple amino acids that are found in prebiotic chemistry. It uses 10 complex amino acids which were invented by biology, and it uses only the left-handed side of it. Well, these kind of choices, 10, 10, and then chirality, would be different on other worlds if life started separately. Right? And this is what we would propose to look. Let's imagine a case where we went to Enceladus, found amino acids in the plume, it was the same 20 that we have here on Earth, but they were all right-handed. That would tell us right away it's a different type of life, because we are all left-handed. Right? So that's why the amino acids are interesting. So I want to do a little, having finished talking about Europa and Enceladus, I want to do a little side trip to Earth. As Linda said when she introduced me, I've been doing work in the Antarctic, and here's a diagram of Enceladus, the plumes, and there's 2 ice-covered lakes in Antarctica that we are studying as analogs for these ice-covered worlds. And particularly interesting ones is Lake Untersee and Lake Vida. In Lake Untersee, there's an anaerobic zone where both methane and ammonia are being produced. It's one of the few environments where both methane and ammonia are being produced that are not environments fueled by rotting meat. If you rot meat, you can make ammonia, but it's because meat is protein rich, and so when it decomposes, it makes a lot of ammonia. But that's not a good model for Enceladus. But here we see methane and ammonia coming out of a microbial system in roughly equal quantities. And that's a good model for Enceladus. And here in Lake Vida as well. But I'm going to focus on Lake Untersee. This is the shore of Lake Untersee and our camp there. And this is a diagram of us taking samples. So you can see my main qualification for these trips is that I'm tall enough to reach the drill. And this guy, Dale Anderson, is a colleague of mine who lives in New York, but happens to be here this week. So I dragged him along, and he's sitting in the back. Don't hide, Dale. And what's interesting about this environment, one of the things that's particularly interesting about it, is we were the first team to open the lake and dive into it. So this is Dale diving into that lake. He was the first human being to see that environment, going into it and see it, which is really an unusual thing. I go to a lot of environments that are out there, but very few of them are places where no one's ever been before. And in fact, not only was he the first human in this environment, he was probably the first vertebrate in this environment. There's nothing but microbial ecosystems in this lake. And it's kind of incredible to think there are still places on Earth that are that isolated. And that's me there. I'm probably saying, Dale, we're leaving now to go get a coffee. We'll be back in about half an hour.
Were you worried about contamination?
No, we're not worried about contamination because this water is 0 degrees and pH 11. And anything that likes to live in me or on me is not going to like to live in 0 degrees and pH 11. So we weren't worried about inoculum contamination, but we are worried about organic material contamination. And so this is the urine collection spot, and the number 2 spot is back here. Every bit of organic material that we brought with us, we carry out with us, because that's the way we could impact this lake. The amount of carbon, organic material represented by this camp, would flood this system with an organic source that they'd never seen before. So it's not the bugs that we worry about, it's our garbage, our waste. And so we carry all of that out. This is, in technical terms, an ultra-oligotrophic lake. Its productivity is very, very low. And so that's the risk, is dumping stuff in it and changing its carbon balance. It's like the fertilizer problem.
What about organisms from millions of years ago, geologic time, that existed in this land?
Well, these lakes aren't isolated profoundly from life. We find, let me get to that question in a second. There's an interesting connection with these lakes. There's actually a couple of them. This is Obersee. The one I showed you was Untersee. They were named by the Nazis, who did the reconnaissance of this area, thinking that they were going to set up a U-boat submarine base in Antarctica. So they did flights. So they were named by the Germans, and apparently they had dropped swastikas out to claim the land. We haven't seen any, but apparently there's in this area. A little bit of interesting military history. But these lakes have geysers, just like, not just like, but they have geysers, which is the way we, in our proposals, try to make a connection to Untersee, and we amplify the relative similarity of the geysers when we're writing the proposals. But in my heart, I know that they're completely different physics. This is gas driven by exsolution of freezing, and Enceladus, it's just water expanding into a vacuum of space. But geysers are geysers, and so we use that in our sales pitches to the reviewers. So there's geysers in this lake. But what's interesting about this lake is the microbial life. Now, these are not ancient organisms that have been separated from the rest of the planet, because microorganisms can be carried by the wind, blown to Antarctica, and literally fall through the cracks in the ice and make it to the bottom. So although we were the first humans, Dale was the first human, and we were probably the first vertebrates, in terms of microorganisms, this lake is, on that sort of time scale, it's in communication with the rest of the biosphere. So we don't have ancient relic life forms here. What's interesting is that they're living here isolated from larger organisms. So we have in a sense, a picture back to what it was like on the early Earth before things like fish and tadpoles that ate these kind of organisms were evolved. So this is how they lived when they could live free. Now they can't, because everywhere they grow, they've got algae eaters going after them, right? So the world is now dominated by herbivores and things, the big organisms that eat those smaller creatures. But here it's not. There's other places which are free of those creatures too, but those places are usually very, very salty or very, very acidic, extreme chemical barriers, whereas here the fundamental barrier is location and ice cover. The pH is high, and that's not good for some organisms, but lots of multicellular organisms would tolerate that pH, as you see in Mono Lake, which has the same kind of pH. Nick, you
What are they like?
what are they like? They're cyanobacteria, and mostly cyanobacteria bats. What's interesting is that they form these mounds, which are really unusual. In fact, I think they're unique to this lake, these mounds, although we see them in the early record of life on Earth. So this is an example of how underneath ice there can be life. Now, in this particular environment right here that we're seeing, this is still photosynthetic. But in the lake, there is an anoxic basin over here where the microbial communities are not light dependent. They are just energy dependent, and their energy is chemical energy. In fact, we're working on a hypothesis that the chemical energy in both of these systems may be related to the release of hydrogen from the weathering of iron that we think is going on in Enceladus too. It's a process called serpentinization, for any of you who are geologically inclined. So I want to move now from the water moons. Europa and Enceladus are getting all the attention because they have water. And water is, we've learned on Earth that water is a good thing for life. But Titan is interesting too, because it's the only other world in our solar system that has beaches. Beaches. What a wonderful thing, right? A beach. You know, a towel, an umbrella, a lemonade with a little tiny umbrella on it. But scientifically, a beach is interesting because it's where liquid meets land meets air. It's an interface. It's a triple interface between air, land, and liquid. Titan is the only other world that has beaches in our solar system. Now, the liquid in the beach is not water. It looks like water, but it's not water. One of my favorite parlor tricks to show this to film crews is to take a cup of water and then take a cup of white gas, like lighter fluid, like barbecue light fluid is white gas. It's a clear hydrocarbon, polar, non-polar solvent, water, and they look identical. But then take a soda cracker and stick one in the water and stick one in the white gas and pull it out. The one that's in the water pulls out, it's just soggy and falls apart. The one that you put in the white gas and pull out, it will still snap in your fingers because the non-polar liquid doesn't dissolve the sugars or the starches in that cracker. So this is not Titan. This is actually Lake Mead. And the film crew took a picture. That's me standing at Lake Mead, pretending I'm on Titan. And you'll notice that the rings of Saturn are tilted, right? But Titan is in the equatorial plane. The rings are going to be edge on. So the film crew, they sent me this still, and they said, this is why I have it. Usually they don't send me anything. But they sent me this still and said, is this okay? They added the clouds and they added Saturn. I wrote back and said, well, you know, technically, Saturn would be edge on and you wouldn't see the rings. But leave it alone. It looks so nice. You know, who cares? Leave it in. It looks much better this way with the rings there than with it done correctly. Since this is late meat anyway, don't sound like you're writing a scientific paper. So leave it in. So that I take full responsibility for why. I never seen whatever got produced from this, but apparently the Saturn is tilted when viewed from Titan. But why is these beaches on Titan are interesting is they cover a good deal of the northern plains, northern part of Titan, the northern seas. These are as large as the Great Lakes. So think of them as the Great Lakes of Titan, and they appear to be interconnected like the Great Lakes. Could there be life in those liquids? Well, the first thing we did some years ago was calculate, is there an energy source? On Earth, the energy source for life is fundamentally light for most ecosystems and photosynthesis. On Titan, living is much easier. The atmosphere makes food for you. Sunlight hits the haze in the atmosphere and creates acetylene and hydrogen, and those don't react, but on the surface, life could catalyze their reaction and get an enormous amount of energy from doing so. So food is coming from the sky if you lived on Titan, living in liquid methane. The chemicals you would need to live are coming from the sky. So what are the possibilities? How do you detect this? And this is problematic because this is not just a case of looking for different amino acids. We're looking for a fundamentally different type of life that's living in liquid methane, not liquid water, at a temperature of 95 Kelvin, which is minus a lot in Fahrenheit. I don't know what it is, but it's minus a lot, right? And how do you even know what to look for? Right? The basic chemical bonds can't be the same. Right? Well, if you think about it, the main manifestation of life on Earth is, in fact, it's pollution. Life on Earth is carbon-based. It lives in liquid water. Carbon is widespread. Water is widespread. Life is widespread. As a result, the pollution of life is widespread. One thing that life does is it metabolizes, it takes in nutrients, and releases waste. And it's not just humans that do this. Right? The original global pollution in our environment was the oxygen produced by cyanobacteria. That was the original environmental crisis on Earth, was the production of oxygen. Now, humans in their wisdom are correcting that problem, getting rid of the oxygen, bringing back the CO2, and restoring the Earth to its environmentally correct initial conditions. Back to nature. Get rid of oxygen, back to nature. But the point is, and even there's other effects. You could look at CO2 in the atmosphere of right out in North America, goes up in the winter when the leaves die and decay, goes down in the spring when the leaves start photosynthesizing, taking up CO2. That's a biosignature. That cyclic release and uptake of CO2 is an effect of life altering its environment. And there's many, many more on Earth. Well, we took the approach of, well, let's look for what those effects would be on Titan. If there was life in Titan, would it have a global effect? If Titan life is carbon-based, carbon's widespread on Titan, living in liquid methane is widespread on Titan, what would the effect be? Well, the answer is it would eat hydrogen. It would consume hydrogen. If there was life on Titan, it would consume hydrogen as an energy source. And so our prediction is that if there was no life on Titan, hydrogen would be constant in the lower atmosphere. And if there is life, it would be eating it to some low level. Unfortunately, we can't get a direct reading from the Cassini for the Huygens probe on that because hydrogen was the carrier gas in the GCMS. But that would be the measurement to do. So if I was designing a mission to search for life on Titan, it wouldn't search for life. It would search for the effect of life on the environment via the consumption of hydrogen. Okay, and that is my clue that it's the end of the talk. And I should thank you for your attention and open up for questions. Question here. I'll repeat the questions.
Is Enceladus losing significant mass from that source?
That's a good question. Is Enceladus losing significant mass from the plume? The calculations suggest that if it lost mass at the rate it's losing it now, over the age of the solar system, it would lose 10% of its mass. So the answer is no. It's not that doesn't limit its ability to keep the plume going.
What's the sample size expected?
Sorry? Oh, the question was, what's the sample size as we go through? It would be very small. As you saw in that artist conception, the collectors are like 1/2 meter in diameter. It's going through a pretty thin plume. So it would be like stardust. Stardust collected little tiny grains, but with modern instrumentation, that's all it takes. So, you know, it'd be small. And that's why I'm confident we can pack it into a return sample, a dumb return sample capsule.
How long will it take, from takeoff to landing?
Yeah, the question on the sample return, how long would it take from when we start the mission to when the sample comes back? It's about 23 years in the best case, right? That's why I talk about these students that I've got working for me. That's why. In 23 years, I don't know where I'm going to be, but I know it's not going to be sitting at the desk. Yeah. Question here? Yeah. What do I want to do next? Figuratively, yeah. Well, that's a really interesting question. You know, what are the interesting things to do next? Let me answer the question by listing what I think are the 5 most interesting challenges for astrobiology in the next 20, 30 years. And I just happen to have that list in my head because I gave a talk recently to a class, an astrobiology class at the University of Santa Clara. And so I said, you guys are just getting out of college, hopefully. What can you look forward to seeing in your, say, 30-year career? And I said, here's my list. 1 is detection of oxygen around an Earth-like planet around another star. High levels of oxygen. That would be pretty cool. Oxygen-rich exoplanet, Earth-like exoplanet. 2nd is evidence of biomolecules for life on Mars. If we find organics deep below the ground, a meter or 2 below the ground, and we find biomarkers in them, like amino acids of a certain chirality. Biomarkers in the plume of Enceladus, as I just outlined. 4 is mirror life in the laboratory. We make life in the laboratory, which we haven't done yet despite the occasional blurps in the media. We make it from nothing, de novo, and the way we know that we've made it de novo is we make it the mirror image of life on Earth. So all the amino acids that are L, we make D. And all the sugars, which are D, we make L. And the DNA curls the other way. It's the exact mirror image of life on normal life. Then we will have created a second Genesis. Now it's a limiting case, but it shows that it's possible. It would also be dangerous. You'd want to contain it. Who knows what it would do if it was released. But you could do that. The technologies for doing that are not that far away. In fact, we put in a proposal. We teamed with the Ventnor Institute to put in a proposal to do that, to take the first step, which is to flip the amino acids. And for those of you that are biochemists, I'll give you a 2-sentence description of what we wanted to do. If you look at biochemistry and say, where does life decide that it's going to be left-handed? Where does it decide? How does it know? Right? There's not a sign that says, please stay left, except when passing, right? So how does it know? Well, there must be some biochemical machinery that knows and makes that selection. And we think that that's the enzyme that brings the amino acids to the protein factory, which is the ribosome. So the ribosome doesn't know. It just merrily staples amino acids together. It's just a stapler. It's the transporter. And the transporter itself is made out of proteins. So if you were to make and it's made out of left-handed amino acids, if you made a D amino acid version of the transporter, then it would transport D amino acids to the stapler, which would then make D protein. So that's what we would propose to do. So just the first step in that direction. So 20 years, it's plausible that we could have in the lab mirror life as one of the first, as a result of synthetic biology. So that's the 4th. The 5th is a wild card, is SETI. Right? And it's becoming a little less wild because The Breakthrough Institute just put $100 million to make bigger ears to listen for signals. That's hard to say it'll happen in 30 years or not, so I put that one in light gray on the list, but it should be on the list because you never know. So those are the things that I one time said I would like to live to see these happen. But now I go running every day, and I quit smoking, and I don't drink, and all that good stuff. But still, I'm not sure I'll see any of them. But those are the things that could happen in 30 years. On the other hand, they do say that only the good die young, so maybe I'll live quite long. Okay, other questions? Question here.
Is there any way to estimate
How old the E-ring is?
Yeah.
No. The question is there any way to estimate how old the E-ring is before observations? Obviously, if you're observing it, you know it's there. But I have not seen any. I've pushed on the geologists and the observers, because being able to say that the plume has been erupting for thousands of years nonstop is a really good argument against people who say, well, you can't launch a mission because you're not sure the plume will be there when you get there. So we've pushed on that and got no good answer. The best they can say is the E-ring, going back to its first observation, the E-ring is pretty unstable. So if Enceladus turned off, the E-ring would go away pretty fast. But there's no other effect on the rings or anything else that we can see that we can argue that Enceladus has been erupting for, say, a couple hundred years. It's not like the red spot on Jupiter, where we know it's been there since, first observations of Jupiter. So we don't know. And if anybody has any good ideas on that, I'm all ears. Yeah.
What do you know that your Enceladus mission is going to be funded?
Well, probably we'll try again the next discovery cycle to put in a sample return. This discovery cycle, we were only able to put in a in situ mission because the sample return problem is still, we can't write a credible proposal that closes the story on the sample return because of the planetary protection issues. So, and it's more than just a technical problem. We have to first come up with the idea, which I think is the right idea. Then the engineers have to work it out. Then it has to be presented to the international committee that makes the rules, COSPAR. And they have to say, looks good to us, and then it gets implemented in the rules, and then we go. So that process will start at the next COSPAR meeting, which is, I think, next summer or something. So we're working it. We're working it, but it takes a while. So most optimistically, we'll put in a proposal the next discovery round, which is probably 2 years, and then if everything goes well, it gets selected a year and a half later. And then 23 years later, hold your breath, we'll get a sample back.
How different do you think life could be besides, you said you could have DNA or not?
Right. Yeah, that's a really good question. The question is, how different could life be? And it's a really interesting and important question if you're going to go search for life, but it's very, very hard to give a good answer to because we only have one example, one data point, life on Earth. There's a fundamental, that's what the tree of life that I showed diagram, fundamental unity of biochemistry. It's all the same. So you could imagine that it could be just a little bit different. So there's things like mirror life, which are different in a technical sense. It's the mirror image, but the biochemistry is the same, it's just the mirror image. So that's one difference. Another difference I was alluding to in the amino acids, where instead of the 20 amino acids we use, life may maybe use the same 10 basic ones and then use a different set of 10 complex ones. But it's still amino acid, water-based life. We would recognize it. We could probably eat it, right? Because we could digest their proteins. Our proteases would break apart their protein, their amino acid bonds. But now you could say, well, maybe it's a little more strange. If there's life on Titan, it's not amino acids, right? It's got to be something else. And I'm actually on the hook to write a paper about what life on Titan will be like, right? So as I'm going running, I think, what could life on Titan be like? And one thing that occurred to me is water. One of the problems for life on Titan, or the people have pointed out, is on Earth, life uses metals as catalysts. So most of the catalysts in your body are proteins which hold a metal, and the metal is the active site that does the catalyst, right? And the protein is sort of the shepherd. And they say, well, there's no metal solubility in liquid methane, and so there's no metal availability on Titan, and so bad news for that. So I thought, that's a good point. Then I thought about it further. Well, let's get completely strange here. Let's use the water molecule as the catalyst. So on Titan, we're used to thinking of water as a medium. On Titan, water is a rock. It's like aluminum. It's a solid. But individual molecules are going to be floating down from meteorites and comets that burn up in Titan's atmosphere. So the strategy I'm going to make up, and this is my first try on it, so depending on how much you laugh, I'll see whether or not it's worth pursuing. So what life on Titan does is it takes water, molecule by molecule, and sticks it in hydrocarbon cages, the way life on Earth takes metals, molecule by molecule. And on Earth, the metals are useful because they mediate covalent bonds. Well, that's because life is based on these covalent redox bonds. Life on Titan can't be because those bonds are too strong. It'll use hydrogen bonds, which are too weak on Earth temperature, but just right on Titan temperature. Well, what is the molecule that masters hydrogen bonds? Well, that's water, right? So water is used as a catalyst. You can turn it this way or that way and show the and control hydrogen bonding. So life on Titan doesn't need metals. Who needs metals? That's so earthly, you know. We're going to use water as our catalyst. So water control. And it's just an example of how you got to think totally weird to conceive what life on Titan might be like. And the objections people list become so Earth-centric when you do that. Now that's not a proof that there could be such life, but it points out to my point that it's hard to answer the question because we're so wrapped up in how life on Earth works, it's hard to get out of that. It's like the proverbial fish in water. We can't even know that we're in water because it's everywhere. So it's really hard. Even on Titan, where we've got a particular case that we're pursuing, liquid methane, it's there, we know what the environment is like, it's still very hard to suss out what the possibilities are. Now go beyond that, other worlds, other solutions, it's hard to be confident that our imagination is up to the task. So I'd say it makes sense to search for water-based life because that's what we know will work, but we should be humble in this assertion that that's the way life is going to be. We may turn out to be freaks in the universe. People will laugh. Those guys live in water. Can you imagine that? You know?
Just kind of curious if is chirality something that can be detected spectroscopically, or is it not?
Yeah. The question is chirality, the handedness, something that can be detected spectroscopically? And it can.
That would be nice because it makes it potentially a remote sensing.
That's correct. That's correct. It potentially can. And in fact, there was a paper recently in Nature which showed that chirality could be detected through the interaction of microwaves on the signal. So microwaves on the system, and by looking at how the microwaves interact and scatter, you can detect the chirality of the sample. And that was a brilliant paper. I didn't understand it really, but I understood it well enough to realize that that is the physics of the tricorder. That's how the tricorder works. If you go to Larry Krauss's book, The Physics of Star Trek, there's no tricorder in it. Look at the appendix, T. No. I wanted to know, what did he, he's got warp drive and photon torpedoes and tractor beams and shields and all this other stuff, but he doesn't have the tricorder in there. There's not even a guess as how it works. It's a great book and Larry's a great guy, but he didn't solve the tricorder problem. So that's been bugging me for a long time. How does the tricorder detect life from orbit? Or, as you all remember, episode 26, about 12 minutes into the episode, Spock uses the tricorder to detect silicon-based life through rock, right? So how does he do that? How does this work, right? Well, this paper in Nature was the answer. It's microwave radiation, which is very good at penetrating things, and it interacts, and the results of that can be detected and the chirality determined, and that is arguably a universal signature of life, that it selects chirality. And your point is very interesting. That could also be a remote detection technique. And to my amazement, I actually found 2 papers in the literature suggesting it as a probe over interstellar distances on other worlds, detecting the polarization signal of scattered radiation on other worlds as a way to detect a chiral signature of vegetation on the surface of that world. So the tricorder, now you say, well, you know, the tricorder was this big, but that's the 23rd century. We still got, what, I estimate something like 30 Moore's Law's timescales to reduce the technology down to that size. So once again, Gene Roddenberry's vision is proven to be correct. And that's not the medical tricorder, by the way, which is a different instrument. This is the astrobiology tricorder. For those of you that know, there's 3 types of tricorders, right? Just to get the record straight. All right, I think that deserves getting kicked off the stage. I agree.
San Francisco Astronomers wants to thank you for the 3rd time we give you this valuable certificate.
Thank you.
And look forward to the 4th.